Welcome back. Let's get into this Laplace domain circuit analysis stuff by finding a transfer function. Okay, so we've got a, oops, I got the wrong problem going. Oh, wait, okay. We've got a time domain circuit here, little v input of t. There's a voltage across this thing. That's our input signal. And then we've got a cap, and then we've got, on the other side of this guy, we're measuring the output signal, also a function of t. This polarity, and this is a 800 nanofarad cap and a 25 kilo ohm resistor. Okay, this is the time domain, just a time domain circuit. So we're given this circuit, and we want to find a numeric value for the transfer function defined by v0 of s over big vi of s. And we want to find, so that's part A, and we want to find B, the poles, right? So it's good to draw the Laplace domain equivalent circuit. So we're going to have big Vi. It looks almost exactly the same, but it's good to take the time to draw these things out here. So this looks like this. Okay, so these are big V's signifying Laplace domain, and so this cap will be 1 over SC, right? And this resistor will just stay R. Now, what we're going to do node voltage. Node voltage method. So the inputs are going to be plus, the outputs are going to be minus, and into the node and out will be plus, and out of the node will be minus. And we're just summing over V. We're summing V over Z terms. So the bottom is grounded here, right? This will be 0 volts, and up at the top, because we're on this side, this is just V0 here, because this is the same node out to this side. And then over here on this node, it's VI. Okay, so we've got a current this way and a current this way. So, so node voltage, let's call this A node. Node voltage at A. It's going to be, so this current right here is the voltage difference over the resistance. So it's VI minus V0 over R. This current going into the node here, and then coming out of the node, it's just V0. So it's coming out, it's negative. And the term is V0 over the impedance 1 over SC. That's equal to 0. So we've got, so we're using R's and S and C's and stuff so that the math is not too ugly, and we'll plug the actual known values back in later. So we can solve for V0 over VI now, because all these others are known. So basically, let's see, so let's multiply this in and move some stuff around, and VI over R will be, and then move these V0 terms over to the other side. It's going to be, well, I'll move the SC to the top, so it's going to be SC V0 plus 1 over R V0. You could factor out the V0, you get V0 SC plus 1 over R. So we can move the VI over and move this fraction over, and you get V0 over V sub I, which is what we're solving for, is 1 over R times 1 over this stuff, SC plus 1 over R. And we can simplify that down by multiplying the r in, and we get 1 over SRC plus 1. Okay, now we want this to be in partial fraction form. Although this is almost an answer, we want it to be in box over S plus box. You know, we need this this thing here, this form, right? So let's see. So we'll take this term here. We'll take 1 over SRC plus 1 and multiply the top and the bottom by 1 over RC, and that'll just give us an S here, right? If we multiply the top and the bottom times 1 over RC, it'll cancel out this RC. So that's going to be 1 over RC on the numerator and S plus 1 over RC on the denominator. So that's our form that we want, S plus something and then something on the top. So we can solve for 1 over RC now and plug those values in. So this is 1 over RC is 1 over 25 times 10 to the third. 25 kiloohms times 800 nanofarads, 800 times 10 to the minus ninth. This is going to be 50. So the answer for A, our transfer function h of s is v0 over vi. It's just plugging in the value of 1 over RC into these two things, you get 50 over s plus 50. That's the that's our numeric value for this transfer function here, 50 over s plus 50, and that's the answer to part A. And part B, the poles are just s equals minus 50. You put in a minus 50 here, the denominator will be 0. That's a pole. That's that.